Hi, we are from PI080, class S07, group number 2. Today we are going to discuss our group project assignment. So the assignment is divided into two tasks. Task 1 is regarding the application of first order of differential equation based on the growth population of North Korea. And task 2 is regarding the application of numerical methods where we were tasked to obtain the root of a function using Newton-Raphson Method with the help of Excel worksheet.
This video explores North Korea population by using mathematical analysis. Despite limited public data, existing demographic figures reveal useful trends. The focus is on examining population growth, age distribution, and related aspects through mathematical models to better understand the country's demographic, even with limited information. It starts with the latest population estimates. The objective of this task is to estimate the population of North Korea using mathematical modeling techniques, specifically exponential functions. Second, to apply the concept of particular solutions in solving differential equations related to population growth. And lastly, to construct and interpret exponential graphs representing the population trends of North Korea over time.
Let's look at this table. It shows the population of North Korea from 2006 to 2025. So the number of population is increasing every year. So that's why we decide to use exponential growth model.
Firstly, from the tabulated data, we managed to plot the graph by using 20 datas of the population in North Korea using the Desmos software. We also graphed the equation using Desmos. The red curve represents our exponential model and the purple dots represent the actual population data of North Korea from the table. If you look closely, the dots almost perfectly match the red curve. That means our equation fits the real data really well. And if we zoom out or scroll back, you will see how the graph behaves over a long period of time. Exponential graphs always rise slowly at first, then suddenly get steeper. This is exactly what we see with population growth. The more people there are, the faster the total population increases.
Let P to the function of t, the number of North Korea population present at the time of t, which is year. Since the rate of growth is proportional to the number of North Korea population, p to the function of t, dp over dt is directly proportional to p, or dp or dt is equal to kp, where k is the constant of proportionality. Next, moving on, 1 over p dp is equal to k dt. Integrating both sides, we got ln modulus of p equal to kt plus c. And then exponent both sides of the equations, and we will get e to the power of ln modulus of p, which is equal to e to the power of kt plus c. Next, modulus of p is equal to plus minus e to the power of c, e to the power of kt. P equals to ae to the power of kt, where plus minus e to the power of c is equal to a. Then, we substitute t with the number 0, which represents the year of 2006, where the population of North Korea is 245,245,07. And we have gotten the equation for 245,245,07, which is equal to a e to the power of k times 0. Thus, we have gotten a, which is the value of 245,245,07. Finally, we have gotten the general solution of our problem, which is p is equal to 245,245,07 e to the power of kt.
Next, 246,463,83 equals to 245,245,07 e to the power of k times 1. Then, e to the power of k equals to 246,463,83 over 245,245,07. Now, we learn both sides. E to the power of k equals to ln 246,463,83 over 245,245,07. Then, k equals to 0.00496. Now we got the particular solution, which is p function of t equals to 245,245,07 e to the power of 0.00496.
T.
From our particular solution, we set the data from t equals to 10, which represents the year of 2016. We found that using the particular solution, we obtained the predicted future and past values. For predicted future value, t equals to 11, which represents the year of 2017, we have obtained the value of 258,99739.31, which approximates to 258,99739 in the population of North Korea. For predicted past value, t equals to 9, which represents the year of 2015, we have obtained the value of 256,44084.04, which approximate to 256,44084 population in North Korea.
Since the calculated value for future value is not equal to actual value, this shows that the particular solution used to estimate the future value at t equal to 11 is inaccurate. Similarly, the calculated value for the past population is different to actual value. This difference also indicates that the particular solution used to estimate the past value at t equal to 9 does not match the actual data and is therefore inaccurate. From the calculated past and future value obtained, we calculate the percentage error for future value, which is 0.32%. Meanwhile, for past value, the percentage error equals to 0.27%.
Although our model is accurate, there are still small differences. That's because the exponential model assumes a constant growth rate. But in real life, many unpredictable things can happen like policy changes, economic problems, health issues, or even natural disaster that can slightly increase or decrease the population growth. So even if the model is close, it doesn't always match the actual data 100%. Several important events and conditions have affected North Korea population growth in the past. First, the famine in the 1990s, also known as the Arduous March, caused many deaths and slowed population growth. Second, the government has strict policies that can control family size and population planning. Next, access to healthcare is limited, especially in rural areas, which affect life expectancy and infant mortality. And lastly, there's almost no migration in or out of the country, so growth only depends on birth and death rates.
In the future, there are a few possible factors that could change the growth rate. If the economy improves, people may have better living standards and choose to have more children. If healthcare gets better, mortality rates could decrease, and life expectancy could increase. On the other hand, natural disaster or climate change like floods or droughts could cause food shortage and reduce growth. Changes in government policy could also encourage or discourage having children. Finally, global events like sanctions or pandemics could impact the country's resources, health, and population growth.
To sum up, we use exponential modeling to represent population growth using the actual data. For task 2, which is the numerical method, so we are tasked to use Newton-Raphson Method to obtain the root of the function square root of x over 2 equal to cos of 1 minus x over the interval 1, 3.5 and state the answer correct to the 5 decimal places. To solve these questions, we use an Excel worksheet to solve the assignment questions by applying the built-in formulas in Excel. Then we drew the graph for the question that we solved using the alternative graph applications. Lastly, we insert the graph in the Excel worksheet.
First, let f of x equals to 0. To find the root of the equation, which is fx equals to cos of 1 minus x minus square root of x over 2. Then, we differentiate the equation and we'll get sine of 1 minus x minus 1 over 4 sed x. We start with an estimation of 1 for iterative x0. Then, if the tangent is drawn to the curve at x0, the point x1 where the tangent crosses the x-axis, a better root approximation compared to xo as shown in the figure. From x1, we produce a new estimate x2 from x1. Then, we produce a new estimation x3 from x2. We move on until we're close enough to the actual root or until it is obvious where we're getting nowhere. The formula of the iterative is xn equals to xn plus 1 minus f of xn over f prime xn. According to the table, the value of our first x is 1 And after the first iteration, our x became 3. After the seventh iteration, the value obtained became constant, which is 1.8283608808, which indicates that it will not change anymore, and it is the actual root of our function. By looking at the graph, we label a few tangents to the curve. We only draw 4 tangents to the curve because the other tangents are too close to each other that make it seems like they are overlapping. But actually, the difference between the tangents are too small. So we decided to only show 4 tangents to the curve, which shows how the tangent line iteratively find roots of the function. To sum up, the actual root of the function that we obtained is 1.8283608808.
That's all from us.
Thank you for watching.